Welcome to the Royal Institution Math Masterclass of Patterns in Primes. To get you warmed up, I've got a little task for you. Charlie wants to know how many factors 360 has. How would you work this out? Pause the video to have a little think about how you would work this out. Right, before we go and have a look at the answer to this, I just wanted to talk to you a little bit about the Royal Institution. The RI is a science communication charity which has been around since 1799. They've got a huge amount of history and lots of famous scientists lived and worked at the RI. Most importantly, they've always been about communicating science to the general public, and that's something they still do today. They do talks and activities for the public, as well as with schools all across the UK. Here are some of the things that the RI does today. They especially have lots going on in London, so if you enjoy your masterclass, there are a range of holiday workshops at the RI which you might like to take part in. Let's start our session then, patterns in primes. What was your method for solving this? The solution is on the slide, but you may have come to it in different ways. Remember, the definition of factor is a number that divides into another number with no remainder. This sets up the next activity, which is looking for prime number factors. For this activity, you will need Worksheet 1, which is available to download with the link to this video. And you'll also need some multi-link cubes. You will need one worksheet between pairs or groups of 3 or 4. One cube represents one unique factor. For each number on the grid, build a tower with the correct number of cubes, one for each unique factor. For example, 1 has only one factor, therefore you put 1 cube on there. 2 and 3 have 2 factors each, therefore 2 cubes on each square. How many would be in the tower for 8? That's right, 4 cubes. 1 times 8 and 2 times 4. Work together and help each other create a complete model of factors by placing the cube towers on the number grid. If you want to speed this up a bit, why not assign different rows to each other to work on so that you do it as efficiently as possible. You might spot a pattern at this point. If not, when you finish, study your city of towers for patterns. Pause the video now to have a go at this. Did you finish? What interesting patterns can you spot on your grid? You might see patterns relating to certain columns, or to primes, or that the height of blocks appear to get bigger as the numbers increase. Which number has the tallest tower? It should be 36. It has the largest number of factors. Which number has the smallest tower of factors or blocks? Why is this? It should be the number 1 because it's only divisible by itself. Which numbers have the next smallest tower of factors or blocks? All the prime numbers have 2 blocks on them. Why is this? Well, it's because they're divisible by themselves and 1. Do all the numbers have an even number of factors or blocks? No, they shouldn't. Some are odd. Why is this? Have a think. Well, for even ones, each factor pairs add up to make an even number. Odd ones have one factor pair that is a square number. For example, 25 is equal to 5 times 5. The factor 5 is only counted once, so total number of factors is going to be odd. Is there a pattern to the numbers that have only 2 factors? Don't worry if you didn't spot a pattern. This question leads on to the next activity where we'll explore this further. This slide shows the solution for worksheet 1 for you to check your work once you've completed the activity. The numbers in red show the number of blocks you should have in each tower. Okay, for worksheet 2, this is available to download next to the link for this video again. You will also need some coloured pencils. I would like you to circle all the prime numbers on the small 36 square grid. You could refer to your multi-cube towers or the solutions for worksheet 1 to help you identify quickly all the primes. Can you now spot any patterns in the prime numbers? Pause the video and have a look. How did you get on? What patterns are created by the prime numbers? The grid shows all the prime numbers circled. Can you spot a pattern? Can we create a rule for predicting prime numbers? Well, not exactly, but they do all fall into 2 columns, so we can predict this will carry on. Recognising patterns can help us to predict. What do all the prime numbers have in common, apart from 2? That's right, they're all odd. If the prime numbers only appear in these 2 columns, ignoring 2 and 3, we might predict that this rule holds for larger prime numbers. What is the relationship? Well, we put them on a grid of rows of 6 for a reason. They are always one more than or one less than a multiple of 6. This is exactly the research of some mathematical experts. You might find it interesting to watch the video linked on the screen. It shows Dr. Vicky Neal discussing what we have been looking at so far. The main detail for setting up the rest of the session is between about 1 minute and 8 minutes on the video. If you don't have time right now, don't worry, it won't affect the rest of the session. In summary, she discusses that there are lots of patterns in prime numbers that are shaded on a 10 by 10 number grid. Even columns don't have any shaded apart from 2 due to the divisibility by 2. 2 and 3 are the only consecutive numbers that are shaded. As the grid continues, the gaps between prime numbers seem to widen, and this makes sense because larger numbers have potential for more factors. She asks if prime numbers eventually stop occurring as these gaps get larger. That's difficult to comprehend and think about, so we use computers to help us. A theorem that has been around for a while states that there are infinitely many prime numbers, and we are sure of this. Vicky explains the proof for this. Her proof is quite complex, but easy to understand with her explanation. In the rest of this session though, we're hoping to find a rule to predict where prime numbers might occur. This is an article from the Guardian newspaper in 2018. It's about finding the next prime numbers and exploring the concept of infinitely many prime numbers. The number shown is a recently discovered prime number, the largest known at the time this article was written. It has more than 23 million digits. So how can we discover new prime numbers? Well, it'd be very difficult to identify all prime numbers in a larger number grid. Eratosthenes' sieve is one of the oldest methods for finding prime numbers, named after a Greek scientist who invented the method. It allows you to try and discover primes for bigger number squares. You will need Worksheet 3, which is available to download with the link to this video. Worksheet 3 is a 100 number square. The first thing you will need to do, number 1, is start by sieving out 1. So can you cross out the number 1 for me, please? Next, sieve out multiples of 2, 3, 5 and 7. Look for patterns of multiples on the grid that are of interest. This will help you to sieve out each multiple with relative ease and get you to do it a bit quicker. So number 2, start from 2, circle 2, but cross out every multiple of 2 from your sieve. So that would be 4, 6, 8, 10, 12, etc. going all the way up to 100. Essentially all your even numbers. Step 3. Starting with 3, circle the number 3, but cross out every other multiple of 3. So you would cross out 6, that should already be crossed out from the 2 times table, but 9, 12, which will already be crossed out, 15, and so on. You might want to pause the videos here to have a go at doing this. Step 4, repeat for the number 5, so put a circle around the number 5, then cross out every other multiple of 5, 10, 15, 20, 25, 30, 35, 40, and so on. And then repeat for the number 7. You won't need to do the number 6 because the number 6 will have already been crossed out due to it being a multiple of 2. Pause the video now to have a go at those. Now that you've had a go yourself, what did you think of this method? How did you feel about doing it? Did it take quite a while? Did you get into a bit of a routine? What are your thoughts? Here are some questions to think about. Which numbers get crossed out more than once and why? Well, they were numbers with multiple prime factors. Which numbers don't get crossed out and why? Well, they were the prime numbers. What pattern on the grid did the 3 times table have? Did you spot that they were diagonal? Did that make you colour them in and circle them a little bit quicker? Why do you not need to test for 4, 6 or any other numbers above 7 in this grid? Well, it's because looking at the numbers on the top row, 4, 6, 8, 9 and 10, they're all multiples of 2 and 3, so they've already been sieved. In other words, we only need to sieve for prime numbers. Also, if you choose a number greater than 10, which is the square root of the maximum number on the grid, 100, its factor pair must be less than 10 and has therefore already been sieved. A bit of a tricky concept to try and gather that one. On the slide at the moment, we have the answers of the ones that were currently sieved out. I wonder if you spotted any patterns. The next set of slides will introduce the next activity of finding even bigger primes using a larger number grid. Use your sieving abilities to find all the primes up to 300 or even more. Let's choose a square number grid that will work best. Which 2 would you definitely not choose? 17 times 17 grid, 289. An 18 by 18 grid, 324 squares. 19 by 19 grid of 361 numbers. Or 20 by 20 grid of 400. Have a pause of the video and have a think. Which 2 would I definitely not use? Well, we definitely not use a grid of 17 by 17 or 19 by 19. This is because these 2 do not have the multiples of 2's in columns, so it'd be very difficult for us to cross out all the multiples of 2's very easily. That leaves us with 18 by 18 or 20 by 20. I think 18 by 18 is best. Do you agree? If not, why don't you agree? Many of you will say 20 by 20 grid because the multiples of 2 and 5 line up in columns, so it's easy to sieve. But I'm going to try and convince you that I'm right, that 18 by 18 is best. Let's compare the 342 and 400 grids. Sorry, 324 and 400 grids. Which multiples align into columns for each? We know the 2's do for both, but what else? Well, for the 18 by 18 grid, It's the 2s and the 3s that go in the same column. And for the 20 by 20 grid, it's the 2s and the 5s. Here are those multiple grids sieved out. For the 324 grid, 18 by 18, we've sieved out 2/3 of the numbers, about 67%. For the 400 grid, or 20 by 20, we've sieved out 3/5 of the numbers, that's 60%. Therefore, there are fewer numbers left to sieve on the 324 grid. So it's better to go, or quicker to go for the option which has less numbers left. It's at this point you'll need Worksheet 4. Again, this is available to download alongside the link to this video. Now you have your grid. Do the first 2 steps of the sieve. Step 1. Circle all the prime numbers in the top row. 2, 3, 5, 7, 11, 13 and 17. Step 2. Sieve out or cross out for 2 and 3 by shading down those columns as shown before. Remember we said that all the multiples of 2 and 3 are in the column, so you can cross those out. Your worksheet should look a bit like this now. All the prime numbers are in the columns with the arrows. One above or one below a multiple of 6 like we spotted before. Let's complete the sieve now. When we did the 100 grid, we learned that we only need to sieve for prime numbers in the top row. Which factors are left to sieve? Well, we're going to look at 2, 3, 5, 7, 11, 13 and 17. For factor 5, there's a pattern we can use. Can you think what it is and how it could help us? Here is one way. Find all numbers in unshaded columns with a 5 in the units or the ones position, e.g. 55 in column 1. For factors 7, 11, 13, 17, which factor pairs do you need to test for to finish? Your worksheet should look like the following slide. Here, the prime numbers are in the white cells. How did you get on? If you want to find the solution at home, you can always search the internet for prime numbers to 500. Marcus de Sotoy, prime numbers make the internet safer. You can watch this YouTube video to find out more. We have managed to predict where prime numbers might occur, in the column one smaller or one greater than a multiple of 6. However, this doesn't help us predict where the next prime number will occur. As Vicky said, powerful computers are doing this for us. Why might we want to know new prime numbers? Well, Marcus helps to explain why new prime numbers are useful. The fact that they are unpredictable forms the basis for online cryptography. That these are not predictable means that our data and financial information is stored safely. Large prime numbers are used as a sort of lock and key system for our data that only the website you are using knows the answer to. If they did become predictable, this data might be at risk of being hacked. So to recap our session, there are infinitely many primes with no pattern. We cannot predict where the next one might appear. There are some patterns to primes that we know about. There's only one even prime number. 1 is not prime. And apart from 2 and 3, all prime numbers are either 1 more than a multiple of 6 or 1 less than a multiple of 6. The unpredictability of primes makes our online data safer. If you want to extend yourself further, why not take a look at this? Another way to visualize factors and primes is shown in this video. When watching, think about which shape is used to represent primes. And why do you think that shape was chosen? You could also think about why specific shapes such as squares and triangles were chosen to order non-prime numbers. If you want to extend your knowledge of patterns of primes further, the links on this slide are great resources. And that's it for me. Hopefully you enjoyed our exploration of prime numbers, and we look forward to seeing you again in the future for another Maths Masterclass.